Okay, class, in this lesson, you are going to use similarity and the geometric mean to solve problems involving right triangles. Okay, so let's go ahead and get started. Okay, there's a lot of information here, but let me go ahead and distill this for you. Okay, so basically what this is saying is if we have this large right triangle up here, and if it's cut into two different right triangles by this altitude, okay, this dotted blue line, okay, that creates two different right triangles, then both of those triangles are similar to the large right triangle, and they're also similar to each other, okay? And how are they similar? Well, they're similar by the angle similarity theorem. Let me show you. So if you take a look at this smaller triangle, right, this is the result of this altitude. This angle A is the same as this angle A in the larger triangle, okay? And angle ADC, so this right angle is also the same as this right angle in this larger triangle. So because we have two angles that are the same in both of these triangles, the smaller one and this large one, then by the angle similarity theorem, we know that both of these triangles, the small one and this large one, are similar. Likewise, this other triangle that results from creating this altitude, we know that angle B here in this medium-sized triangle is also the same angle B in this larger triangle, and this medium triangle has this right angle here, right? Angle CDB is a right angle. And in this large triangle, angle ACB also has a right angle. So by the same theorem, similarity theorem, where both angles are the same in both triangles, we know that both this medium triangle and this large triangle are similar. Okay, so said in a very simple way, when you take a right triangle and you create two right triangles as a result of an altitude, then you create two triangles, two smaller triangles that are similar to the large triangle as well as to each other. Okay, so that's what this theorem 9.4 says. The altitude to the hypotenuse of a right triangle divides, right, cuts into two different triangles that are similar to the original triangle. So I'm talking about the larger triangle. They're similar to the original triangle and to each other. Okay, so let's go ahead and take a look at an example. So here we're going to find the missing length within the right triangle. We're going to find the missing length of QS. Okay, now how do we do that? Remember, as I taught before, that the order of these letters representing this triangle, PQR, is very important because there's a relationship between triangle PQR and triangle QSR. Triangle QSR is here, QSR, okay? So if we establish their ratios, okay, meaning if we say that PQ over QS is equal to QR over SR, okay, then we can go ahead and use this ratio to solve for QS. Now, how did I establish this? Okay, here's what I did. I took the first two letters of this triangle, PQ, and I set that over the first two letters of this triangle, right? PQ over QS. Now, why did I pick those? Well, we know the length of PQ, and we're trying to solve for the length of QS, okay? And I set the ratio of QR, which is this, over SR, which is this, right? These are the last two letters of this first triangle and the last two letters of this second triangle. Now, why did I pick those? Well, we know the length of QR is 15, and we also know the length of SR is 9. Then, if that's the case, then we know this, we know this, we know this, and we can solve for that. Okay, so the important thing is to establish this ratio correctly. Once you have that, then we can replace those letters with their respective lengths. Okay, so PQ we said is 20. We don't know what QS is because that's what we're solving for. We know QR to be 15 and SR to be 9. Okay, so then we can go ahead and cross multiply these, QS and 15 and 20 and 9, and we'll find that 15 QS is equal to 20 times 9. Okay, that means QS is going to equal 180 divided by 15, or QS is equal to 12. Okay, and so there is our answer. So we're using similarity to identify and solve for the length of QS in this example. Okay, so let's move on to another example. Now, there is another way to solve for different components of a right triangle that is divided by an altitude, okay? And that is the geometric mean, okay? Geometric mean. Now, what is the geometric mean? Well, let's say that we have this ratio, A over X is equal to X over B. If we were to cross multiply these, okay, cross multiply these, you'd find that X squared is equal to AB. And then solving for X, we'd have to square root both sides. And we find that X is equal to the square root of AB. This is our geometric mean. Okay, geometric mean, meaning X is equal to the square root of the product of AB. Now, how does this apply to the right triangle? Okay, well, let's take a look at this triangle ACB. Okay, ACB. We see that triangle ACB is the large right triangle, right? And if we wanted to solve for X here, okay, CD, right? So we want to know what CD is. We would use the similarity ratios that we did in the previous example, okay? And what that means is we would take the ratio, we would find that this triangle, let's take a look here. Triangle CDB, okay, triangle CDB, okay, is similar to ADC, okay? If you think about it, we're going to take CDB and just rotate it clockwise by 90 degrees. So if I were to rotate this triangle, okay, and compare it to this, then that final triangle would be right about here. Let me go ahead and shorten this a little bit. It's drawn a little too large here. All right. Oops. It's being a little finicky here. Okay. Okay. So this becomes C, D, B. This is a right triangle. Okay. And we are looking for X, right? So this is my X value for this triangle, and this is also my X value for this triangle. But because we rotated it, my X is also over here, which is side CD. So if we were to use the similarity ratio, we would say that 6.4 over X, right? 6.4. So this side to this side is going to be equal to this side of this medium triangle. This medium triangle to this side, which is also 3.6. So right in here is 3.6. So that ratio is going to equal X over 3.6. Okay, hopefully that makes sense. That might have been confusing for some of you, but hopefully you can see how when we take this triangle and rotate it 90 degrees, I'm just putting it on top over here, okay? Now we have this scenario, 6.4 and 3.6. Okay, we're gonna cross multiply those. So if we cross multiply this and cross multiply this, we see that x squared is equal to 6.4 times 3.6. Okay, so then x is going to equal the square root of 6.4 times 3.6. And that works out to 6.4 times 3.6. And we take the square root of that. X is equal to 4.8. Okay? We can use this similarity ratio to solve for x, or let me go ahead and erase what I drew here in blue. Okay? And go back to the original equation. Okay? So if you take a look, if we want to solve for x here, all we have to do is take the product of 6.4 and 3.6, right? Because that's what we did here, and then take the square root of that, and now we have x, right? So instead of going through all of this ratio stuff, we can just take the geometric mean, which is x is equal to square root of a times b, okay? And say that x here is going to equal the square root of 6.4 times 3.6, and my x works out to 4.8. See how much easier and faster that is if we know the formula? Okay, so that is how we apply the geometric mean to this particular example. Okay, now the key thing here is to recognize that this length here is the hypotenuse of this larger triangle. Okay, and this hypotenuse is divided by, or split into two pieces by, this altitude. And if we want to know the length of this altitude, then all we have to do is to multiply the lengths of that split, take the square root of it, and now we have the answer. Okay, now, so here's the corollary 1 to theorem 9.4, basically explaining what I just said. The length of the altitude of the hypotenuse of a right triangle, okay, so the length of the altitude is the geometric mean, meaning this stuff here. The product of these two lengths right here, okay, is the geometric mean of the lengths of the segments of the hypotenuse. So this segment and this segment, multiply those together, take the square root of the product, and you now have the length of the altitude. Okay. Example 4. Okay, we're going to now use the geometric mean to solve for both the length of RT and ST. Okay, now instead of using variables, I'm going to use actual numbers now. Okay, so in other words, let's say that we're solving for the length of RT, and I'm going to call this X, and then we also need to solve for the length of ST, right? ST, and we're going to call that Y. Okay, so to solve for x, watch this. We're going to use a geometric mean. X is equal to the square root of, now what numbers are we going to put in here? We're going to take 9.6 times 9.6 plus 5.4. Okay, now what did I do here? We're solving for x, so we're going to take the segment of the altitude that is adjacent to x, or closer to x, which is 9.6. And we're going to multiply that by this entire length. This is why I have 9.6 plus 5.4. So we're going to multiply by this entire length, and that'll give us x. Okay? Similarly, if we want to solve for y, okay, watch this. Y is going to equal the square root of, and we're going to take the segment of the hypotenuse that is closer or closest to y, which is 5.4. So we're going to take 5.4, and we're going to multiply that by this entire length of the hypotenuse, which is 9.6 plus 5.4. 9.6 plus 5.4. And now we'll have the length of side y. Okay, so let's go ahead and finish calculating x and y. So we punch those in the calculator. We get 9.6 times 15. 9.6 plus 5.4 is 15. And we take the square root of that, and we find that x is equal to 12. And then for y, we're going to take 5.4 and multiply that by 15, and then we're going to take the square root of that, and we find that y is equal to 9. Okay? And that is how you solve for the base of this large triangle, the height of the large triangle, and the altitude of this triangle. As long as you have the segments of the hypotenuse, you can use the geometric mean to solve for this, and this altitude. All right, hopefully that made sense. If any of this was unclear, please go back to the beginning of the recording and listen to this again. Thank you.